So this is a course, so it's called Mathematical Geoscience, and the aim of the course is really to use mathematical models, relatively simple mathematical models, to describe and understand aspects of the natural world. We're going to do that mostly through differential equations. There's some more seats around here if you want to come round the back. We're going to mainly use differential equations, so ODEs and PDEs, and we're going to have quite a lot of physics and chemistry that we need to sort of translate into the language of differential equations and then make some sense out of it. And the course is going to be divided into three main parts. The first section is going to be about climate, and we're going to start that today. So we're going to build some very simple climate models, and in particular models of the carbon cycle. And then the second section will be about rivers, and we're going to talk about how we can predict floods. And then the last section of the course will be about ice, which is a very important part of the climate system, and which has some interesting dynamics. So we're going to talk about that at the end of the term. So I'm going to start with the first lecture. We're going to talk about a very simple question, which is what is the average temperature of the Earth's surface, or the average temperature of its atmosphere, and why? Okay. Now, obviously that varies depending on where you are on the Earth, and it varies over time. But we're just going to talk about what's the average. Okay, and the average temperature at the moment is around about 15 degrees centigrade. Why is it 15 and not, say, minus 60 like it is on Mars? Okay. Now that turns out to be mainly a question about radiation. Radiation is the transfer of energy by electromagnetic waves. And we receive radiation from the sun, lots of it, but we, the Earth, also emit radiation back out to space. And we do that at a rate that depends on our temperature. And that leads to a kind of an equilibrium, or at least the possibility of an equilibrium, where those two things can balance each other. And that turns out to be the main thing that determines the average temperature. So the first section of the course is going to be about radiative balance models. And I'm going to start, as I often do, with a picture. So here is the Earth. The Earth we're going to treat as a sphere with a radius r. It's going to turn out not to matter what the radius of that is, but it's about 6,400 kilometers, the radius of Earth. And I'm interested in the atmosphere, which I'm going to treat as a very thin sort of spherical shell around the planet. And I'm going to treat this as having a thickness which I'll call d, which is going to be about 10 kilometers. I'll talk about that a bit more later on. And okay, then somewhere over here is the sun. So this is the sun, and that is emitting radiation towards us. The sun emits what we call shortwave radiation. So that's these are electromagnetic waves that have a relatively short wavelength. In this case, it means that they're in the visible part of the spectrum. We can see the light from the sun. It's light, but also a lot of what comes from the sun is ultraviolet, which we obviously can't see, but is transmitting a lot of energy. And that contrasts with the radiation which the Earth is emitting. So the Earth is also emitting radiation. We can't see that. That's because it's not in the visible part of the spectrum. It's mostly in the infrared part of the spectrum. We call this long wave radiation. And that's because the Earth is at a lower temperature than the sun, and lower temperature objects tend to emit longer wavelengths of radiation. Okay, so what I'm going to try and do is to write down an energy balance model for the heat that's contained in the atmosphere. Okay, and so importantly, there's going to be some radiation coming from the sun, I'm going to treat that as a constant, and I'm going to call this capital Q. It is about 1,000, let me get the number right, about 1,370 watts per square meter. Okay, watt is a unit of power. Per square meter means this is the amount that's coming and hitting us per square meter that we look at. Now, a certain fraction of that just gets reflected back off the Earth and doesn't get absorbed by the Earth. So some of this is kind of useless to us because it just bounces back off. And that's a fraction which is called the albedo. So there's a certain amount that just gets reflected back off again, which I'm going to write as A times Q, where A is something called the planetary albedo. This is a word that we're going to talk about quite a bit. And this for Earth at the moment is around about 0.3. And it depends very much on what the surface looks like. It depends on how dark it is. So if you imagine one of those pictures that you will have seen of the Earth from space, you'll see that the oceans look very dark, and the deserts and clouds look quite bright, and ice caps look quite bright. So where it's brighter, it's reflecting more sunlight. That means the albedo is large. And where it's darker, in the ocean and forests, it's absorbing more, and the albedo is lower. And so this is like a global average. Which for Earth is about 0.3. Okay. Now, then the Earth is going to emit radiation, and that depends on the temperature. I'm going to call the radiation coming from the Earth QE, and I'm going to have to write a bit about this, which I'll do over here so we can see the picture still. So I'll say Earth emits radiation, and we're going to introduce a piece of physics here, which is something called the Stefan-Boltzmann law, which tells us how a surface at a certain temperature emits radiation. So I'm going to say, according to the Stefan-Boltzmann I think Boltzmann might have two N's, law for what we call a black body. Now the Earth is not black, but the black body is the word that gets used to describe a surface which is not internally heated, which doesn't have some reactions going on inside it. Okay, and I'll tell you what this Stefan-Boltzmann law is in a second. We're going to have to modify this to account for the greenhouse effect, because this tells us how much gets emitted from a surface, and some of what gets emitted from the Earth's surface gets absorbed by the atmosphere and then re-emitted by the atmosphere on its way out. So only a fraction of what gets released from the Earth's surface gets out to space, and that's the phenomenon that you will hopefully have heard of, called the greenhouse effect. So I'm going to introduce that in quite a simple way here, which we'll see. So I'll say modified to account for the greenhouse effect. So I'm going to write this QE is going to be gamma times sigma times T to the power 4, where T is going to be the temperature of the surface. That's what I'm aiming to try and find. This sigma is a constant called the Stefan-Boltzmann constant. So this is about 5.67 times 10 to the minus 8 watts per square meter per Kelvin to the power 4. So that's just an empirical parameter that's comes from the Stefan-Boltzmann law. And the gamma is a greenhouse factor. So this is how we're modifying it. Gamma is going to be less than 1. Is the greenhouse factor So that's the fraction of radiation that's emitted from the surface that actually makes it out to space. Okay. That depends on the composition of the atmosphere, because what the atmosphere is composed of determines how much of this long wave radiation gets absorbed. And in particular, you'll be aware that this depends on the concentration of greenhouse gases, which are particularly good at absorbing certain wavelengths of radiation. So obviously it depends on concentration of CO2. In fact, more important in some ways is the concentration of water vapor, which is an important greenhouse gas, and it depends on various other things like methane and other gases that occur in smaller concentrations. And we're going to talk a bit more about some of that in later lectures. Okay. Right, so what I'm now going to do is, using all of that, I'm going to write down an energy balance equation for the heat that's contained in the atmosphere. Okay, so we're going to write down energy balance for the atmosphere. Okay, and so what I'm going to write down is that the rate of change of the heat content of the atmosphere is going to be equal to the amount of energy that is gained coming from the sun minus the amount that's emitted through radiation out to space. This is like a conservation law, conservation of energy. So I'm going to write down the rate of change, and then I want to write down what's the heat content of this atmosphere. Right, I'm going to write that as the volume of the atmosphere times the heat content per unit volume, which is proportional to the temperature. Okay, so first of all I need to say what's the volume. I'm going to approximate this because the atmosphere is so thin compared to the radius of the Earth. I'm just going to take the volume to be the surface area of the Earth times the thickness. You have a question? Yeah.
But the temperature, we assume, I think, the average temperature is like on the surface, but in thinking about just height, the temperature is low. I wonder why
This is a great question, because I'm going to talk about that later on in the lecture. So the question was the temperature should vary with height in the atmosphere. And that's certainly true. So the temperature generally gets colder as you go up through the atmosphere. So we're being extremely crude here. We're just going to say that the whole thing is roughly at the same temperature. And then we're going to talk later on about, obviously it's colder at the poles than it is at the equator. And that's because there's more sunlight arriving at the equator than there is at the poles. And it varies with the height as well. So we're going to come back to that. But for the moment, I just want to know what's the average everywhere. It's also not right to say that the atmosphere is of a definite thickness. It's actually quite hard to define what the thickness of the atmosphere is because the air just gets thinner and thinner as you go out towards space. So that's also kind of an approximation. Yeah, thanks. So bear with me, and then we'll come back and make it more detailed. We'll do the simple things first. So I'm going to write down the volume of this spherical shell, and I'm going to say that that's going to be 4 pi r squared times d. Right? I hope that makes sense. There's an approximation in the volume. And then I'm going to multiply by the density of the air times the specific heat capacity of the air times its temperature. I'm just going to make a note. So the density of the air is also not a constant, but I'm going to treat it that way. It's about 1 kilogram per cubic meter. And Cp is another physical constant, which is the heat capacity of the air, which is around about 10 to the 3 joules per kilogram per Kelvin. We're going to need those in a second when we try and work out some numbers. Okay, so this is the rate of change of this energy Okay, this is going to be equal to the amount of energy we absorb from the sun. Now this was an energy flux. It was watts per square meter. So I need to multiply it by the area that it's been received over. If you think about the geometry here, if we're standing on the Earth looking at the sun, the area that this thing is hitting is a circle of radius r. Okay, so in fact maybe it's better to imagine standing on the sun and looking at the Earth, right, and you'll see the Earth as a circle of radius r. So here we're going to have pi r squared times q times 1 minus a, because a fraction a of it got reflected back off again, so it doesn't get absorbed. Okay, so that's what's coming from the sun, and then I'm going to subtract off the radiation we emit out to space. This is emitted from the whole surface area of the Earth. That has surface area 4 pi r squared. So I'm going to have 4 pi r squared times this rate. So this was in watts per square meter. So gamma sigma T to the 4. The temperature, by the way, this is going to be important in a second. In this Boltzmann law, the temperature has to be in Kelvin, right? It's proportional to the temperature to the power 4 for reasons that are not entirely obvious, but that temperature has to be the absolute temperature. Okay, so this is now a differential equation for temperature T that we're going to solve. We're going to treat everything else as a constant. We can simplify it a bit. If you notice, there's factors of r squared everywhere, so I can just get rid of those, and pi as well. So I'm going to rewrite this. I'm going to write it as capital C times dt by dt is going to be equal to, I'm going to divide by 4 as well, a quarter q1 minus a minus gamma sigma T to the 4. And capital C is just some constants that I've grouped together. That's going to be d rho Cp. We can think of this as like an integrated heat capacity of the atmosphere. Which in fact allows us to kind of get away with the fact that rho is not really constant and d is not really defined. If we think of d times rho actually as being the depth integral of the density of the atmosphere, that is a kind of well-defined quantity. Okay, and that has a value that is around about 10 to the 7 joules per square meter per Kelvin. Okay, so this is our first very, very simple climate model, and it only includes radiation, but it's enough to tell us at least roughly what the temperature of the planet is. Like, I'm going to treat everything in here as a constant apart from capital T, so it's quite a straightforward ordinary differential equation. And the first thing that you should think about differential equations like this is whether they have any steady states. This one has a steady state. A steady state's a solution that's independent of time, so that term would be 0. So that's when we have a balance between the radiation from the sun and the radiation emitted by the Earth, and that tells us what the temperature should be. So we have a steady state. I'm going to call that T0. Okay, so just by rearranging that, that's Q times 1 minus A over 4 gamma sigma, all to the power of 1/4. Now, if we didn't have the greenhouse effect, this gamma would just be 1. We wouldn't need it. So I'll just make a note about what happens if, in that case, if gamma were 1, that's what would happen if the Earth didn't have an atmosphere. then if we put in the numbers that I've given you here, we'd find that this T0 is about 255 Kelvin. It's about minus 20 Celsius. So if that was the case, then most of the planet would be frozen. If we go the other way and say, well, we kind of know what this temperature should be because we can measure it, and I told you earlier on, it's around about 15 degrees centigrade, so it's about 288 degrees Kelvin. So actually, maybe I should just make a note. Around 273, roughly, Kelvin is the same as 0 degrees Celsius. So the observed average temperature, which is around about 288, keeps going up, obviously. That suggests, and we're working slightly backwards here, that suggests that this greenhouse factor must be around about, now if you put in the numbers, you get about 0.61. If you remember, that was the fraction of what's emitted from the Earth's surface that gets out to space. And obviously, as you increase the concentration of greenhouse gases in the atmosphere, what you're doing is decreasing that gamma, which is slightly confusing, that when you make the greenhouse effect stronger, you decrease this greenhouse factor. That's just the way that it's been defined. And that, as you decrease gamma, then that obviously makes this temperature go up. Okay, and that's a very simple explanation of global warming. The second thing that you should ask if you have an ODE like this, having found that it has a steady state, is whether that steady state is stable or unstable. This one, it turns out, is stable, which is a good thing, because otherwise it wouldn't live in that steady state if it was unstable. So, is the steady state stable? And the answer is yes. And I want to show you two simple ways that we can see that. That you will hopefully have seen before, but this is just techniques that we're going to use quite a lot in this course. So I want to make sure that you're familiar with these. The first is a graphical method. And so this we're going to just plot, according to that equation, we're going to plot dt by dt as a function of t. Which is what this equation tells me. dt is this function of t, which is a constant minus constant times t to the 4. So it's just a quartic, which is going to look something like that. The steady state was defined as where dt is 0, so that's where this line crosses the axis. So that was t0. And what you can see from this graph is that if you were at some temperature that is less than T0, then dt by dt is positive. So what will happen is that the temperature will increase and you will move this way. And you'll move this way until you get to that point. So if I were here, I would move, the temperature would increase and I'd move towards that point. If I was over here at a larger temperature, dt by dt would be negative. So my temperature would decrease and I'd come back this way. So wherever I start, I'm going to always end up at that point. That shows that that state is stable. And generically for this type of differential equation, if you've got the graph crossing the axis going downwards, then it's going to be a stable steady state. Okay, the second method is slightly more formal, and that is a linear stability analysis. And So you hopefully will have seen this idea before. So the idea is that we're going to perturb ourselves from the steady state by a little bit, and then we're going to look at the dynamics and work out, does that perturbation decay or grow over time? And that tells us, in this case, it's going to tell us that we decay back towards the steady state. So we're going to do that by writing the temperature as the steady state temperature plus a perturbation. I'm going to call that perturbation T primed, where T primed is small, by which I mean it's much smaller than the steady state value T0. And then we just stick that into the equation. The equation then, so T0 is independent of time. T primed is the thing that depends on time. So we have dt prime dt is equal to 1/4 of Q1 minus A, those were just constants, minus gamma sigma T0 plus T prime to the power 4. And because T primed is small, we're going to linearize this term, this non-linear term. We're going to approximate it using the fact that T primed is small. That's basically like doing a Taylor expansion, or in this case a binomial expansion. So that's going to be quarter Q1 minus A minus sigma gamma T0 to the 4 minus 4 sigma gamma, right in the same way around, gamma sigma T0 cubed times T primed plus higher powers of T primed. I'll write that as HOT, higher order terms. And then, but if T primed is small, those terms are going to be small. So we can ignore them, and we just get this bit here. These two terms exactly cancel out by the definition of T0 being the steady state. So that term and that term cancel out. So this is an approximation now. Approximately minus 4 gamma sigma T0 cubed times T primed, and we just ignore the higher order terms. So we have linearized the equation at that point. The reason for doing that is that if we have a linear equation like this, then we know that that just has exponential solutions. Right? dt by dt is minus some constant times T primed. That just has a solution which is proportional to the exponential of minus that constant times T. So T primed is proportional to e to the minus, I'm going to write this as T over T0, where T0 is that constant, which is C over 4 gamma sigma T0 cubed. But this is a time scale. When I've written the exponential like this, it's the time scale over which the perturbation decays. So this tells us two things actually. First is that it tells us that this perturbation decays in time because there's a minus sign there. So that means that this is a stable, steady state. But it also actually tells us a bit more because it tells us how fast can we expect it to decay, which for these sorts of problems is quite a useful thing to know because it tells us how quickly would we expect the system to respond to a perturbation. If we work out using the numbers what this thing is, this turns out to be about 30 days, which means that the atmosphere, the temperature of the atmosphere responds relatively quickly, depending on your perspective, to a change. So if the sun were to double its strength, it would get hotter quite quickly, for example. That's obviously not likely to happen. But for example, when there has been huge volcanic eruptions in Earth's history, that's put loads of ash into the atmosphere, that has the effect of changing the albedo, because that blocks some of the sunlight. So it means that we don't receive as much sunlight. And that leads to a cooling over that sort of time scale. So that's something quite useful that comes out of doing that. Okay, So that's obviously an extremely simple model. Later on, we're going to come back. In fact, over the next couple of lectures, we're going to kind of make this more complicated. In particular, we're going to think about how other things, apart from the temperature here, could vary in time. So that the radiation coming from the sun, the Q, it doesn't change that much, but it does change a bit, partly because the Earth's orbit's not completely circular. The albedo can change a lot. That we talked about the fact that depends on what the surface of the Earth looks like. So that can change, especially depending on how much ice cover there is. And that's partly why the Earth's climate's changed a lot in the past. And this gamma, obviously that can change with the composition of the atmosphere. And that's something that we're doing a kind of large-scale experiment on that at the moment, obviously. But we're going to talk a bit about how we can actually predict gamma from considerations of what's going on in the atmosphere. And then this will then tell us what's the temperature changes that we can expect from that. This model can also be applied to other planets, and if you look at the problem sheet, I think the problem sheet asks you to think about what happens with other planets, where the main difference is that you have a different Q, because if you're a different distance from the sun, you have a different amount of radiation that reaches you. Okay, so I want to move on, and let's do this over here, to come back to the question that was raised about the fact that the temperature really varies with height in the atmosphere. So I'm now going to talk about the vertical structure of the atmosphere. So in reality, the temperature and the density, which we're treated both of those as just single values here, they really depend on depth. And let me just sketch roughly how they do depend on depth, and then we'll talk about why that is. So I'm going to plot the density rho as a function of height z. This is roughly exponentially decaying. So it looks something like that. And its value at the surface is the value that I used earlier on. It's about 1 kilogram per cubic meter. So you'll be aware maybe that if you climb Mount Everest, the air gets pretty thin at the top, which is why you generally have to use oxygen. And that's a reflection of the fact that the density is much less. And then I'm going to plot the temperature also as a function of depth. This is in some ways kind of more interesting, actually. So the temperature does get colder as you go up. It actually reaches a minimum at some height, and then turns around and increases again, and then reaches a local maximum and then decreases towards outer space. This minimum occurs at around about 10 kilometers height. It's somewhere called the tropopause. So this is around about 10 kilometers. And it's around the height that a plane usually flies, at least a big plane. I don't know if you know the temperature outside a plane. They used to, in the olden days, they had told you on the screen on the aeroplane what the outside temperature was, which is usually about minus 50 degrees centigrade. I'll call it 220 Kelvin. Here, this is at the ground. This is where it's around about 288 Kelvin at the moment. Obviously, this depends also on latitude, which I'm not worrying about here. At least this value does. The region below this tropopause is where most of the weather happens. That's where we form clouds. That's where we have storms and so on. But if you fly, you're usually above the clouds. This is called the troposphere. And that's the region that I was really thinking of as the atmosphere in the first model that we wrote down. This is where most of the contents of the air contents of the atmosphere is. But there is some bit above. This bit above here is called the stratosphere. And you do sometimes get some clouds up there, kind of high clouds. and then this local maximum called the stratopause, and then above that there's the mesosphere, and then there's various other spheres as you get higher where the atmosphere is really, really thin. So most of the interest of so weather forecasters and so on is with this troposphere down here. Okay, so why do they look like this? And this can be understood with some quite simple pieces of physics. So let me try and explain some of these. Okay, so the question is why? Okay, so the first thing that we need is the ideal gas law. This describes behavior of a gas, which the atmosphere obviously is. And this says that there's a relationship between the pressure and the density and the temperature of a gas. And it says that the pressure is rho RT divided by MA. At least that's how I'm going to write this. This is the density times a constant times the temperature divided by another constant. So R is called the universal gas constant. That's about 8.3 joules per kilogram per mole. And MA is the molecular mass of the atmosphere, which this is averaged over the, all of the composition of the atmosphere. And this is around about 29 times 10 to the minus 3 kilograms per mole. A mole, if you remember your chemistry, is a measure of an amount of a substance. Well, this is really the molar mass, I guess. Molar mass of the atmosphere. Okay, so this symbol here is a P, that's the pressure. This symbol here is a rho, that's the density. In this course we have lots of pressures and densities, and they can look very, very similar. So I try to put a sort of stalk on the top of my P, and I try to make my density very rounded to make it a rho. But just be aware that we're going to talk about P's and rhos quite a lot, and you need to try and find some way of distinguishing them. T is, again, temperature has to be measured in Kelvin for this to work. Okay, so we're going to use that. I'll call that equation 1. Okay, the next thing that we need to know is that the atmosphere is roughly in hydrostatic equilibrium. That's a concept that comes from fluid mechanics, which we'll talk about a bit later on. It's equivalent to saying that we have a vertical force balance where the pressure at any point within the atmosphere is proportional to the weight of all the air that's on top of it. And this is not exactly true, but it's a very good approximation for how the pressure varies with height in the atmosphere. Seem to have chosen a pen that doesn't rub off. Give me a good workout. We'll come back up here. Okay, so the next thing that we need to know here is that we have hydrostatic equilibrium. Okay, this is an approximate vertical force balance. And we're going to express this with the differential equation dp dz is equal to minus rho g. So this is the rate of change of pressure with height is equal to minus the density times gravitational acceleration, g, which I haven't written down anywhere. So g is about 9.8 meters per second squared. Okay, I'm going to call that equation 2. So we can understand, just with these two pieces of physics, we can understand why the density looks like this, at least roughly, because the temperature, although it varies, it doesn't vary by that much on an absolute scale. So if we treat this temperature as a constant, then this ideal gas law just says that the pressure is proportional to the density. So if I stick that in here, the pressure is proportional to a density, then I can basically replace that with a d rho dz, and then this equation says d rho dz is proportional to minus rho, which gives me an exponential solution, or an exponential decay with z. So if we treat temperature as roughly constant, now obviously this is not that great an assumption, because it's not that constant, but it's not too bad. So roughly constant then if we stick equation 1 into equation 2, we'll get d rho dz is equal to minus mag over r T0 times rho. I've just rearranged to get this stuff here is all then I'm treating as a constant. Okay, and that gives me that rho is some constant, let's call it rho s for rho at the surface, times e to the minus, and I'm going to write this as z over z0. It's a bit like what I did before, where z0 is just this constant. So z0 is going to be r T0 over mag. And I'm writing it like that because this has got something that's got units of length, and it's the height scale over which the density decays. So if we put in the numbers, this is around about 8 kilometers. Okay, which ballpark is similar to the 10 kilometers height of the tropopause, and that's why I used that value of 10 kilometers as the depth of the atmosphere in that very simple first model, right, because that's the length scale of which the density decays. This is sometimes called the scale height of the atmosphere. It's a term that gets used a lot in meteorology. Okay, then the last thing that I want to do today is try and explain, I'm not going to explain all of this, but I want to explain this temperature decrease here within the troposphere, and for that we need an energy equation. So that the last piece of physics we need is the energy equation. We already wrote down an energy equation for the whole atmosphere, that was this thing over here, but now I want to do it sort of depth dependent. And when you do that, it turns out radiation is not so important. Actually, advection of the air, so that's movement of the air, and compression and decompression of the air are the things that are the most important. So I'm going to write down a more complicated looking energy equation. This is going to be, I'll write it like this, rho Cp times capital D by dt of t minus capital dp dt is going to be equal to the divergence of k grad t minus the divergence of some q. So this is a form of the heat equation that you might have seen before. This term here represents conduction. In the air, that term turns out to be really negligible, so in fact I'm just going to ignore it. We're going to include that term in some of the other models that we look at. This term here, you might not have seen before. This term is absorption and emission of radiation. So Q here is the radiative energy flux. Now this was really important on the scale of the whole atmosphere, but it turns out not to be so important like locally. So I am at least within the troposphere. It is more important in the stratosphere. So this is radiation, and this is not such a great approximation, but I'm going to ignore that for the moment as well. These terms here, this capital D by dt, if you haven't seen this before, this is something called a material derivative. So maybe I'll just make a note here. Capital D by dt, this is again a concept from fluid mechanics. This is the rate of change with respect to time following a fluid particle. So you can write this as partial d by dt plus u dot grad t. U is the velocity of the fluid. Gradient of t means the gradient in space. So this represents the rate of change following the fluid. And the same thing here. And in the troposphere, this does turn out to dominate this equation, well, partly because there's nothing else left, so it kind of has to. And that's because in the troposphere you have a lot of convection. This is why we get interest in weather. Convection represents vertical motion of the air in the atmosphere, and that causes this equation to be dominated by the vertical advection terms that appear in here. So there's the vertical velocity times the vertical gradient in the temperature, and the same thing in the pressure. And that turns out to dominate these terms. So I'm going to say in the troposphere, convection, the convection is driven by the fact that the air is hotter. We're not going to get into this, but the air is hotter lower down, and hotter air generally is lighter and therefore wants to rise compared to colder air, and that sets in motion some convection. Vertical advection to dominate. Okay. And so if we average over time, the time dependence here is quite important, but if we ignore time dependence, just to understand what's the sort of base state, then we're going to have here rho Cp times dt dz minus dp dz is approximately 0. Right. So the vertical advection causes the z derivatives in these two terms to dominate and to balance each other. So I didn't say this term here represents heat, the heat due to the compression or expansion of the gas. So as you change its pressure, that changes its heat content. That again, if you've seen fluid mechanics for like a liquid, you generally don't have that term because it's very small. But in a gas, that's important, particularly on this scale. Okay, so this is the approximation of the energy equation. That I'm going to call equation 3. And if I combine that with equation 2, which has come off the top of the board, equation 2 told me what dp dz is, minus rho g. So I can put that in here, and then that's going to tell me what dt dz is. If I rearrange it, it tells me dt dz is minus g over cp. So two constants. This I'm actually going to give a name. I'm going to call it gamma, capital gamma d, which is the name it's often given. This is what's sometimes called the lapse rate. It's the rate of change of, actually it's, I think there's a minus sign there. It's the rate of change of temperature with respect to height. So it's how quickly does it get colder as you go up. And if we put in the numbers, this turns out to give us around about 10 kelvins per kilometre, if I use those units. So if you go to the top of Ben Nevis, which is order a kilometre higher than sea level, then the temperature is about 10 degrees colder on average. Okay, now this actually, I've ignored something here which does turn out to be a bit important. This gamma D, the D represents dry. So what we've done here is to ignore water vapour. And it turns out that the condensation of water vapour to form clouds in the atmosphere is quite an important term in this energy equation that I didn't write down. So although I crossed out various terms that I didn't think were important, I actually ignored writing down a term which is important. And that's because I don't want to talk about that yet until next week, when we will talk a bit about how clouds form. But they do affect this. So this is how the temperature varies when there's very little water vapour in the atmosphere. When there's water vapour, that turns out to change this slightly, and you get actually a slightly lower rate of decrease of the temperature with height. Okay, so that's it for today. On Wednesday, we're going to talk about modelling the greenhouse effect in more detail. So we're going to try and work out what this gamma actually is. See you then.